Welcome to the Earth Science Classroom. We're looking at a little bit of volcanoes, a little bit of geomorphology, a little bit of plate tectonics and the Wilson cycle. I'm looking at LIPs, all right, and what they are. Looking at plateaus and how they form and different types, and also the flood basalts or flood traps and what they are, and how they link into both LIPs and plateaus. So LIPs are large igneous provinces. Now, in terms of geology, this is a big deal because they're showing a large area that's covered by layers, and they can be, vary in thickness of each layer, and cumulatively can be very, very large. And they can create plateaus because of this. Large area of igneous material. Now, this is going to be derived or, originated from very large lava flows. And we can carbon date, we can get the absolute and relative age of these, pretty much basaltic lava flows. Now, we've discussed basaltic lava flows a lot in volcanology and tectonics, and in terms of igneous rocks, in relation to mid-ocean ridges, volcanology, and we know that basaltic are generally mafic, which is high in magnesium and iron. They also have high rates of movement, so very high volumes, like fissure volcanoes, for example, in Iceland. And we know that there is very low viscosity, which then is low gas content, which again links to how fast and how the rate of the movement, and also the high temperature. And when they condense, consolidate, crystallize, they form these large areas of basaltic rock in nice bedding and strata. And we can observe these around the world. In terms of locations, some articles state there's over 90 plus locations around the world, both on continents and oceans, varying in size and scale and thickness, and also date of when these were formed. Now, the majority of the of articles I read in textbooks I read regarding the starting point. Now, a lot of these LIPs started around the Mesozoic era, so around 250 million years ago, up to about 65 million years ago, which corresponds nicely with the breakup Pangea. So we can also include Wegener's theory. TESC is for spreading, Wilson's cycle of supercontinents and breakup and creation of oceans. We can also link up in terms of continental rifting and how they form. So the types, now in terms of the oceans, they can form seamounts. They can also form ocean basins and fill basins. They can also form ocean plateaus. Okay. Now, in terms of the continental LIPs, there we do get the flood basalts over certain continents, certain lands. And we also get involved with the passive plate margin, which is in relation to continental rifting and the Wilson cycle, stage 2, where the ocean starts to form through seafloor spreading. and the subsidence and thinness of the crust due to the tensional stress applied by rifting. And that's going to cause, once the crust gets thinner and weaker, you get some faults forming, some dikes, and you get the presence of magmatic material rising to the surface and fill in the new basin, the new half or full graben, with new igneous material. So they're the locations, and again, we have discussed a little bit of plateaus in the ocean formation and also the flood basalts. Okay, so how are we going to link these in? So the LIPs, that's kind of like the umbrella term. That underneath that, is going to be the plateaus and flood basalts. So we look at plateaus and their characteristics. This is in relation to geomorphology, volcanology, and plate tectonics. Looking at generally flat land, it's raised relief and elevation, so it's higher ground, and pretty much it is formed through crustal shortening. Now, what does that mean? It means that we have convergence. Convergence and collision between two plates or two land masses, generally continental. And we have the thrust faults, which are encouraging there to be splays and ramps, of which the rock layers can move and overthrust and basically build the mountain through orogeny and through increased mass. So as they're getting squeezed together through compressional stress, right? So it's like this. So one side is in that way, one's that way, so you get collision, and you get this crustal shortening where the only way to go is down to increase the root, according to Airy and Pratt, or mostly Airy, in 1855. All right, and also upwards to create orogeny and higher elevation and high relief. So this is getting shorter. It wasn't stretched, it's compressed, so it's getting shorter. At the same time, it's getting thicker with more mass. Okay, and you're going to get obviously have isostasy as well, playing its part with the flotation and buoyancy between the balances and forces. So this is crustal shortening, and these plateaus can form. They can form behind, so it can form here and get pushed. So it depends on which one's more dominant in terms of the collision. You get this high level of relief and land directly behind a large mountain range or a large craton, which is a very old part of the continent, and you get this high kind of like plateau right here. And the classic example is the Tibetan plateau, which is behind the Himalayan mountains or Himalaya mountains. So the Himalayan mountains is that narrow range of mountains, which is very high elevation of over 29,000 feet. Then you get behind it that kind of flat, elevated land right behind the Himalayan mountains, which is the plateau. Now, generally because of orographic rainfall, because of the rain shadow effect of high relief mountains kind of blocking the rain from getting to the leeward side, not the windward side of the mountains, you do get kind of desert conditions. And the perfect example for that is the Atacama Desert, which is smashed between two different mountain ranges, and it's high relief as well. Another way of making a plateau is called thermal expansion. That's basically the introduction of a diapir, which is a raised head or raised inclusion of usually magma underneath the crust from the asthenosphere, or a mantle plume, which is in relation to hotspots mostly around the world. So you have your crust, right, and you have your asthenosphere, so your plate, and then you have this this raised kind of thermal expansion coming up like this, and then the corresponding effect is for this part of the crust to be raised up through uplift, okay, and you get this raised flat area according to the amount of plume activity underneath and the amount of uplift from the asthenosphere. You get this kind of like plateau being formed because of thermal expansion. So that leads me to the types, right? So there's plateau types. There's formations. There's what it is. It's flat land. It's raised relief. There is the formations. So this is how it's formed. Two ways. So put 1 and 2. Now the plateau types obviously relate to the formations. Is going to be 1, okay, or put type A, dissected plateaus. Okay, which is our crustal shortening. Okay, so that's that one there. Okay, purple. And then the other type is going to be, all right, B type, which is going to be volcanic plateaus. So directly linked with thermal expansion and the introduction of magma, either under or on top of the surface, which would include lava. Now, in terms of lava, like we discussed, we're looking at the discussion or description of flood basalts, or occasionally called traps. All right, so what are flood basalts? All right, flood being like in terms of the water where it goes everywhere, like floods everywhere and sprays everywhere and kind of fills the whole area with water. Now, replace the water with lava. All right, so mafic lava or mafic lava, which will basically it's basaltic lava, which will turn into the igneous rock basalt. Now, this is extrusive, low in silica, low in viscosity, and very fast running high temperature. But it is not just the average fissure eruption like you get in Iceland, but it's just those short durations, like in terms of thousands of years, where there's just consistently a large amount of magmatic material coming out of the crust, and it's linked to certain locations. Now it's linked to hotspots, and it's linked to research has shown that it's kind of like these flood basalts occur at the beginning of this mantle plume journey. And what I mean is this: you have your crust, your plate. You have your asthenosphere, and then you have your mesosphere, and some of these plumes are suggested to form even as far down as the core mantle boundary. You have these plumes. You have this like little tail, and then it plumes up like this. Okay, could have one, you could have multiple, but there we go. And this is in addition to the regular convection current model and mantle movement model that we have. And what will happen is you're going to get this initial burning through of magma from what's called the plume head up here, and then the tail, which links down to the deep parts of the mesosphere and asthenosphere, where the source of magma is going to come from. Okay, and some even indicate there could be a remake of old subduction slabs of old ocean crusts coming back up. It's a recycling process, basically. And it comes up, and it's just that initial explosion of all this magma that's flowing out in great distances, hundreds of kilometers in some cases. And it layers up over time and makes these really high plateaus of these very horizontally formed beds of basalt. and it's like the first stage of the hotspot. And then once that's over, obviously the plate is still moving through convection currents and still moving. So once it moves, you get more of a consistent flow, like basically unplugging, a Coke bottle or soda bottle. There's an initial spray of all this, gas and soda. And then once it calms down, you get the more consistent flow of soda out of the bottle. It's the best kind of analogy I can think of to explain it. And then also you get the regular hotspots stuff like a Hawaii or Galapagos or Yellowstone, where you get that consistent, very forming shield volcanoes or fissure volcanoes, where you get more consistent hotspot activity and the creation of island chains like Hawaii and the Emperor Seamounts. So good examples and case studies you can use in your classroom with kids or in college is the Deacon traps in India and the Columbia River basalts in USA. So actually in Washington, Oregon, Wyoming, okay, as well. Now, so first, the word trap, that's just a term given to a single or specific province, right? So province is a large area. So this particular large area is in India. We call it Deacon traps. Now, it formed around 65 million years ago, and pretty much, well, they say that also the most recent is 2 million years. But also it gave out, or currently is basically 500,000 square kilometers. Okay, that's quite a large area. But it started out for things had eroded and weathered and moved through tectonics, actually 1.5 million square kilometers. So large, not the largest, but still a very large and famous area to study geology and these flood basalts. Obviously, close to home, USA, the Columbia of the Northwest, you're looking at a system of about 7 formations within this basaltic system. Okay, and you've got the Oregon Plateau as a big one, and you have the Columbia Basin as well. Now this runs around or near the Columbia River, okay, and is linked to, well, Deacon traps is linked to the Reunion, I can't spell it, but Reunion Island hotspot, okay, I was going to spell it right, and it has migrated over the course of 65 million years from that location. Now it's oceanic hotspot, but before it was where India was, and it formed the Deacon traps. Now, the Columbia River basalt is a bit different. This is linked to the current Yellowstone caldera and hotspot, whereby the North American plate has been moving at a southwesterly direction and has moved to its current location in Wyoming, but was further west in the past, and that's how these flood basalts in this region of northwest America was formed. So this was like 350 lava flows over the course of a few million years, so 16.7 to 5.5 million years ago. So over that time, that's 11 million years, there was a ton of lava flows and created a very thick layer of basalt. Now, Deacon traps is over 6,500 feet in elevation, so very high, over 2,000 meters. Whereas the Columbia River Basin is about its thickest is 3,500 feet thick at its thickest. So these are very large plateaus, flat areas formed by large voluminous basaltic lava coming out over a short duration in certain locations. We call these traps, and they're great areas to see where there was rifting, where there was plate tectonics and also the breakup of Pangaea and how they moved from various hotspots around the world that we can clearly see today, both in the oceans and the continents. All right, so I hope you guys enjoyed this. We can link this into both volcanology and tectonics and geomorphology, and also the theory of, Wegener and Hess and Wilson and all those theories with tectonics. All right, guys, thanks a lot.